Okay, so welcome everyone to our paper session 38 on debt. My name is Alejandro Martin Gomez. I'm with the University of Arkansas, and I'm going to be your session chair for this paper session. So today we have 4 presenters that will have 12 minutes to present and an additional 3 minutes for Q&A. And today, and I will try to do my best to introduce all the presenters. So today we'll start with Hae-Jeon Kim from the Korea Advanced Institute of Science and Technology, KAIST, who will be presenting the paper toward a more standardized multi-directional tapping task in VR, the effect of target depth.
Good afternoon, everyone. I hope you all had a great lunch. My name is Hae-Jeon Kim from KAIST. It's quite exciting and making me nervous at the same time, since it's my first time giving presentation in front of this many people. So I try hard. So today I'm going to present our work titled Toward a More Standardized Multi-Directional Tapping Task in VR, the effect of target depth. Let's begin. In HCI research, evaluating the efficiency of input devices and interaction techniques is an important task. So in this regard, the multi-directional tapping task, also known as 2D feature task, has been widely used as an evaluation method. Recently, an increasing number of research papers have adopted the multi-directional tapping task as part of their experimental methodology. And additionally, as VR become prevalent, the multi-directional tapping task has been also widely adopted in prior research in XR environments too. But unlike 2D interfaces, in XR environment, there is one additional variable, which is depth. So previous studies have manipulated this depth variable in 3 main ways usually. First, by changing only the target size and the fixed depth, similar to 2D interface. Second, by changing both the target size and target depth at the same time. And third one is by adjusting target size based on visual angle and also changing the target depth at the same time. However, these different approaches to manipulate depths gonna cause some kind of problem. It's gonna make harder to compare and generalize previous research results across studies. And we believe one of the main reasons of this issue is the lack of investigation into the lore of depths. And this motivated us to investigate the depths more in a structured way. So based on that motivation, the first research question we aimed to investigate was how does depth affect performance in multi-directional tapping tests? So to test this hypothesis, we designed an experiment where we vary target depth while keeping the target size constant. Participants performed the multi-directional tapping task at 4 different depth levels and 3 different target widths and 3 different target amplitude, using 2 representative interaction methods, which is raycasting and virtual hand. In addition to performance metrics, we also collected many behavioral data, such as controller movement, cursor movement, eye movement, and also subjective feedback. So we recruited a total 20 other participants for the study, and the experiment setup is shown in the following image. To isolate the effect of depth differences, we intentionally simplified the experimental setup, such as we eliminated some depth cues like shadow or ray length, or we make light minimally. As you can see, participants were seated in a chair and performed the multi-directional tapping task while remaining in a place. So move on to the result part. It was quite obvious, although the target size was constant across both methods, like depth had a significant effect on all performance variables. Like for raycasting, showed a sharp decline in performance at like closest and furthest distance, which is like 0.5 meter and 10 meter. But like interestingly, at 10 meter, the R-square value like sharply declined. And for virtual hand, showed a decline performance in like movement time and throughput at 0.3 meter and 0.6 meter, which is like closest and furthest. Like as I mentioned earlier, we collected like a large amount of behavior data, but we have like limited time today, so we won't be going into the details during these presentations. Like for those who are interested in details, please refer to our paper to depth discussion. So what I'm going to do is like long story short. For raycasting, when it's too close, participants had to raise their arms significantly, and this led to increased hand movement and less stable cursor control. And also, since the target were often outside the participant field of view, since it's too close, they required additional eye movement to locate the target. And when it's too far, when target appears smaller due to increased depth, we observe longer fixation duration and more unstable cursor movement. And these effects became more pronounced as the distance to the target increased. Like for the virtual hand, when it's too close, they often force participants into unnatural posture, such as like they make them to lean back to see the target properly. And this discomfort led to frequent error during the task. And when it's too far, we observe increased fixation duration and more unstable cursor movement, and this caused them to more like movement time. So it was quite obvious that like depth had an effect, but like while our initial experiment helped us understand the general effect of depth, we recognized the need for more like detailed investigations. Specifically, we wanted to isolate the effect of depth by controlling the target bezier angle, so that target would appear the same size regardless of distance. This allows us to examine how depth alone influences performance independent of perceived size. The experiment setup was identical to that of experiment 1, but the key differences was that we adjusted the target bezier angle so that the targets appear the same size across our depth levels. So we used 4 depth levels and 3 target widths by adjusting with target bezier angle, and 3 different amplitude with adjusting by target bezier angle. So experiment 2 results are quite interesting. Like even though targets had the same bezier angle across all conditions, so it appears same in every distance, we still observe the clear effect of depth in both interaction methods. Like for raycasting, there were clear differences between the 0.5 meter, which is closest condition, and all other distances across our performance metrics. However, like no significant differences were observed between distances beyond 2 meters. So there was no differences were observed between 2 meter and 10 meter and 100 meters. In terms of virtual hands, significant differences were found across distance condition in terms of movement time and error rate. But different to experiment 1, there was no meaningful differences were observed in throughput. So experiment 2, like for raycasting, when it's too close, similar to experiment 1, participants had to adopt awkward controller posture, such as like higher controller height, and which led to unstable cursor movement and increased eye movements. And these factors collectively contribute to decreased overall performance. But interesting thing is, after a certain distance, since it looked like same, appears same, when bezier angle remain constant, depth itself has not affect performance and even user behavior. But the virtual hand part is like, it's similar to experiment 1. Placing target either too close or too far led to physical discomfort, and which results in significant differences in error rate and movement time, but not in throughput. So what we want to say from our experiment is like, even with the same type of interaction, outcome can vary depending on the depth. And this highlights the importance of carefully considering distance as a factor when designing experiments. So in our study, in raycasting, like when the visual angle is kept constant, testing at depths of 2 meter or greater yield consistent results that are not affected by depth. But while experiment at closer distance, like 0.5 meter, must take into account the performance degradation caused by depth. For virtual hand, the optimal performance zone is between 0.4 meter and 0.5 meter, which are not affected by physical discomfort. But researchers should be aware that even small changes in depth can significantly impact performance metrics. Our limitation, this is our last page. So we only use like MetaQuest Pro, so one devices. So it can be different if you use another device. And we overly simplified environment, like we get rid of many depth cues, like shadows or lights. And we only this experiment in certain depth range. So future work's gonna be something can complement this limitation. For example, study in complex visual environments and test broader depth range. And also we didn't consider like participant individual difference, like such as arm length or those things. So in future works, it's gonna be great to consider individual differences too. Thank you for listening, and feel free to ask any question.
Okay, thank you. Thank you very much. I think we'll have some time for questions. Do we have any questions from the audience?
Thank you for good presentations. I have one question that how did you control the target size as the distance increased? Because the more far conditions, participants can perceive the more smaller size.
Experiment 1 or like experiment 2, like I quite didn't get your like question.
In the first experiment, your experiment control the target distance.
Yes.
As these conditions, I think participants perceive target size is more smaller for this reason.
That's what we tried to do. Like we wanted to show, like in first experiment, we didn't adjust the target visual angle. We just put absolute size. So in first experiment, it is obvious that like participants see different distance and different size. That's what we did. And second experiment is like we adjust the target visual angle. So in every depth, participant gonna see the same size of target. That's what we tried.
Okay, thank you.
Okay, do we have any more questions? We have time for additional questions, so. Okay, then I'll probably ask a question. So I understand that you change the size of your objects depending on the depth to make it constant, right?
Yep.
Did you also change the diameter of the circle where you were placing the targets as a function of the depth? So then it will have a similar size depending on the object, on the depth?
Like in experiment 2, right?
So you have your circle with targets, right? When you change the depth, did you also increase the diameter of your distribution?
The distance, the target distance.
Okay.
Which we call like target amplitude.
So what they were always seeing at some point was the exact same similar size.
Yeah.
Okay. Okay, if we don't have any more questions, then let's thank again to our presenter. Our next presenter is Yahu Luo from the Beijing Institute of Technology in China, and she will be presenting the paper entitled Influence of Object Height, Shadow, and adapting luminance on outdoor depth perception in augmented reality.
Good afternoon, everyone. My name is Jia Hongluo. I'm a PhD student from Beijing Institute of Technology, and today I will present the work of my teacher, Shining Ma. And the title is Influence of Object Height, Shadow, and Adapting Luminance on Outdoor Depth Perception in Augmented Reality. Depth perception relies on many physiological factors like binocular disparity, convergence, focus adjustment, and motion. Among this, the binocular disparity is the most important and widely used in 3D displays. Among this, the environment also provides lots of depth cues like perspective, occlusion, relative size, and shadow. These cues help our brain to judge the depth more accurately. In augmented reality, people see both the real world and the virtual object at the same time. So a key requirement here is that the virtual and the real object must match in depth for a natural experience. Many previous studies have shown that the virtual optic properties like size, brightness, transparency, and shadow will influence the depth perception in AR. What's more, the environmental factors like illuminance, size complexity, and additional depth cues also play an important role. Our study focused on the object height, and for its influence, there is a very important explanation called the ground contact theory. It suggests that the distance perception depends on the ground continuity. When this continuity is broken, and the depth error will increases as the height rises. And there are also studies shows that the shadows and contact cues also decrease the depth error. However, this theory was based on the condition that participants don't know about the height information. We don't know will this trend change with the known height. Because the effect of previous height knowledge hasn't been systematically tested, it became a focus of our study. And a few studies have researched the brightness contrast in outdoor AR. So our study conducted 2 outdoor experiments. The first one is the effects of height knowledge, object height, and shadow. And the second one is optimal ambient luminance for outdoor depth perception. Here are our experiment setup. In our experiment, we used Microsoft HoloLens 2 in an outdoor environment, and the average luminance was measured. We used the depth matching experiment, and the virtual object is a single cube. The reference are the wet strips on the floor. The participants should adjust the cube until it matched the wet strip on the floor, and the reference distance was set at 3 levels from 2 meter to 6 meter. Each experiment repeated 3 times, and there are in total 34 participants together. Before the experiment, for accurate depth in AR, we set the HoloLens 2's IPD to match its participants' eyes. And at the beginning of the depth matching task, the virtual object was placed from 1 meter to 9 meter randomly. And the participant should move the cube along the z-axis until it matched the reference white strip. After that, the matched depth was recorded. And here are our experiment 1, height and shadow. This experiment focused on the object height information, and shadow. For object height, we set 3 levels from 0 centimeter to 20 centimeter. And for height information, half of the participants saw object height information in a prompt box, but half didn't. And for shadow, the object was displayed with a shadow on the ground or without one. There are in total 18 and 36 trials together. And to measure the depth error, we use the signed error. It means that the matched distance minus the target distance. If the signed error is larger than 0, it means that the AR object will look closer, so it is an underestimation. Otherwise, if the signed error is less than 0, it is the overestimation. Okay, here are our results of the experiment 1. We use an GLMM to measure the effect of each factors. And we can see that the height and height information both have significant effect on the depth, but the shadow didn't. This result is only for the main effect, and the interaction effect will show in the following page. First, we can see from the first figure for object height. When the object was on the ground at 0 centimeter, the sign arrow is positive. And at 10 centimeter, we can see that the arrow is almost 0. And at 20 centimeter, the sign arrow is negative. This means that as the object gets higher, people tend to overestimate the depth more. And we can see from the second photo for height information, the blue line means with the height information. People who know about the height information will underestimate the depth, but for people who don't know about the height information, they will overestimate them. However, the absolute error didn't get smaller even if people know about the height information. This means that providing object height information only shifted the error direction from overestimation to underestimation, but didn't improve the accuracy. After that, we used Bonferronian correction to test the interaction between different factors. And all the following 4 pairs both have the significant interactions. First, let's see the height information and the object height. We can see from these 3 photos, with the height information, the sign arrow keeps stable in all the height levels. But without the height information, the sign arrow will increase as the height rises. This means that knowing object height information can enhance the stability of depth estimation. Second, we can see the height and the shadow from these 2 photos. And for the floating object, the sign arrow keeps stable with all the height level, but the arrow will be influenced significantly without the shadow. And this effect was only pronounced as the floating object. For the object on the ground, the effect is not so pronounced. So this means that the shadows will enhance the accuracy of depth judgment of only floated object. And finally, for height and distance, we can see that when the height increases, the change of depth arrow with distance became more pronounced. And here are our experiment 2, ambient luminance and environment. In this experiment, we focus on the environmental condition and backlight luminance. We set 3 outdoor environments with different field of view types. Scene 1 is an open view space, Scene 2 is a relative wide view space, and Scene 3 is a narrow view park. Different environments have different average luminance. We use 3 different films to control the ambient luminance transmittance and to get different luminance level in one scene. The object was set at 0 centimeter. And here are the results of our experiment 2. First, let's see the average sign error. It is positive. And this result is similar to our experiment 1. For the object on the ground with height information, people tend to underestimate the depth of them. And for ambient luminance, it has significant effect on the depth error. When the ambient luminance increases, the sign error will increase too. This means that in outdoor environment, if we decrease the hollow latitude transmittance and the depth estimation accuracy will be improved. This is because the environmental brightness contrast is improved. For environment, because the environmental differences among the 3 senses was not fully controlled, so the environmental effect is not analyzed here. Okay, in conclusion, our experiments explored the factors influencing depth perception in outdoor AR, and the main conclusions are as follows. First, with height information, the AR depth was underestimated, but without it, it was overestimated. Second, in outdoor scenes, higher ambient luminance level reduced the accuracy of depth estimation. Third, the presence of cast shadow significantly improved the depth accuracy for floating objects, but had little effect on grounded ones. These findings enhance our understanding of depth perception in AR and support better display design for outdoor environments. That's the end of my presentation, and if you have more questions, please contact with this email. Thank you.
Okay, so with that, we have a few minutes for questions from the audience. Do you have any questions? No questions? Okay, I do have a couple of questions. So for your study one, I was kind of surprised that it seems that the height plays a role in the estimation, particularly in the sign error, right? I think the graph that you were showing when the cube was 10 centimeters high, the sign error seemed to be closer to 0. Do you have any idea why this could be happening?
Okay, so because this photo, we fixed all the with shadow or without one, with information or without the information together in this photo. So if the 10 centimeter is almost 0, it can't say that maybe the 10 centimeter is the best height. I don't think so. Yeah.
I think my question was, I was expecting when the cube was closer to the floor to lead to the smaller sign error.
Sorry, could you rephrase your question?
It's okay. I think it was mostly like it was most like a comment, because I'm surprised to see on your left graph your sign error is close to 0 when the cube is 10 centimeters high,
Yeah.
regardless of the depth, right?
Yeah.
And I was wondering if you have any idea about like why that's happening, particularly when the cube is 10 centimeters high and not when it's at 0 or 20.
Okay. In fact, this experiment is only qualify as the result, but we in fact didn't know about the behind the reason of this result. So maybe I can't give you an actual answer now, and I will think about it after the presentation. Could I get back to you after this?
That's okay. Thank
Okay,
you.
Thank you very much.
Do we have any other questions from the audience? We still have a couple of minutes. Okay, then would you mind if I ask a second question? For your study 2, you tried the 3 different levels of luminance with the augmentations, right?
Yeah.
Do you think that the luminance of the actual environment from the real world will play a difference on the estimation of the object's depth? Like if the environment itself was a little bit darker or lighter, do you think that will play a role on the estimation of the depth?
Yeah, because we use outdoor environment, and you can see that the average luminance is very high for our luminance of the AR. So if the luminance is very high, we can't see the object very clear. So we use different film to decrease the luminance of the environment, and I think that it makes the VR cube looks very clearly. So maybe the accuracy will improve because of this.
But that also depends on the luminance of how bright is the real world, right? Like if you test it at different times, then the contrast between the real and the
in fact, we fix the environment time at the same time of 1 day, and the weather is fixed too. We choose the cloudy weather and without the strong sunlight to control the environment and fix the average luminance. Yeah.
Okay, Thank you very much. Okay, so we'll continue our session with Do-Young Kim from the Korea Advanced Institute of Science and Technology, and he will present his paper entitled Viewpoint Tolerant Depth Perception for Shared Extended Space Experience on Wall-Size Display.
Okay, hello everyone. My name is Do-Young from KAIST Augmented Reality Research Center, and today I'm going to present our work, Viewpoint Tolerant Depth Perception for Shared Extended Space Experience on Wall-Size Displays. And I want to say special thanks to my co-authors, Jin-seok, Hee-jung, and my advisor, Eun-taek. Yes. So this project starts from the project what I'm currently leading. So this is called Meta Museum Project. So what I'm developing with my research team is how can we make the next museum in metaverse? So what will be the experience in that museum? And now I'm currently collaborating with NYU. So KAIST and NYU are keep collaborating on this project. And what I'm currently focusing on is how can you bring this museum experience in New York to Daejeon? So we have, of course, like huge time difference. And also, if it's an exhibition, there should be the room size might be also different. But what I want to enable is how can you enable this meta museum experience through like this huge wall display? So the problem I focus on this research is when I go to museum like this is what I've taken in Metropolitan MoMA in New York. So as you can see, if it's like famous artwork, they're going to be huge audiences in here. So in this case, it's really hard to afford this amount of HMDs for all participants. And I've also experienced of like conduct like this kind of VR exhibition. And in that case, as you can see, all participants have to make a queue for waiting to experience this. So the research question I focused on this is how can we enable this multiple users to experience immersive virtual content in museum and exhibition? So yeah, as you can see, what I focused on is kind of enhancing the ability of this like large wall size display. So what I focused on is a wall display based XR space, which could provide acceptable depth perception, which means not really precise one, and with this wall display and without any HMDs or trackings. So the overview is we utilize a wall display to extend a virtual space image with a visual cues for a three-dimensional representation based on universal viewpoint, which means that assume that participants is located on the center of the screen. And we try to verify the acceptable level of depth perception user could achieve regardless of their distance from the sweet spot. So through the research, we figure out that users perceive depths ranging from 23 degrees to 37 degrees in one side. So it's about like 50 to 70 degrees. They can still feel depth perception, even if it's just an image of this stereoscopic image. So based on the analysis of these results, we derive design implications and directions for wall display-based XR spaces. So there are like a bunch of related works. So maybe you guys maybe comes up, but the first thing is that some system like this cave system, which means utilize this whole room as so without HMD, it tried to convince this a virtual environment experience. But the thing is, it requires a head tracking or eye tracking, and it's also focused on the single user. So it's really hard to applicable for multiple users. And the other solution, there is some special display system that can have some special panels backside. So we can enable multiple users could perceive somehow depth perception, but which cannot be applied for this already installed, like this projector-based or LED wall displays. So my physical environmental setup was like this, with the BIM projector on the side, and the screen, the size of the screen was about 4.2 meters by 2.36 meter. The resolution is about like 70–80% of 4K. The rendering setup, I turn off the light, and only the directional light, which rendered by the Unity, can just appear through the projector beam. And the image is just static image, and we assume that eye height of 1.5 meter, which means this photo which is taken by the virtual camera, which have a 1.5 meter height, and these have some visual cues for 3D perceptions like these shadows or light sources. And we assume we set this the center of it as the sweet spot so that people can perceive it as some depth perception through this image. So for the study design, there are two independent variables. The first is the absolute viewing distance, which means the distance from the person to the object in the extended space through the wall display. And the second independent variable is virtual depth, distance from the display to the object in the extended virtual space. So which means from the display to the extended one. So this is the virtual depth. And we use three metrics. The first is perceived distance difference, which means from the absolute viewing distance minus what participants responded as like how far from it, like perceived distance. And the second metric was a viewing angle threshold, the acceptable viewing angle range that people can feel depth perception. And the last one is perceived presence, which includes realness, spatial presence, and visibility. So yeah, let's go through this by step. So when the experiment starts, participants come into this space, and I'm gonna ask them how far away does the artwork in the center of the screen appear to be. So before asking this question, I provide them the reference lengths for 1 meter, might be this length. I show them this is the 1 meter, and after they see and they answer to this question, so like it looks like they will be about 2.4 meters away from this theta in the center. So after that, the viewing angle threshold for this, I asked them, did the works on the screen appear to be placed with a sense of depth within an extended space? So at the center, most of them might feel somehow depth perception through this image because it's induced to provide a depth perception in the center position. So they say yes. So this is two alternative force choice methods, which means they can only answer yes or no. And then we'll just keep asking these questions. And if they say no, this data can be utilized for estimating the threshold of this viewing angle threshold. And to prevent the effect of gradually increasing or decreasing, which means the participants will get used to it, we use the staircase method to avoid that factor like this. The algorithm automatically just move back and forth to ask the same questions. And through this, we can distinguish the depth perception zone through this angle, which means the people on this zone can somehow perceive the depth through this wall display in an single image in a wall display. And after all this repetition, they're asked to answer the realness, spatial presence, and visibility questionnaire. So yeah, this is the whole loop how I conducted this user study. So this research goal was the study aims to leverage human depth perception to allow users to perceive a single image displayed on a large wall as an extension of their physical surroundings. So our first hypothesis was the perceived distance difference will increase as virtual depth increases and absolute viewing distance increases. The second one is as the virtual depth increases, the viewing angle threshold will decrease. The last hypothesis was the ratio as the dV to the A increases, which means as users move closer to the display, the realness, spatial presence, and visibility will decrease. So for designing the study, there are 6 conditions: the absolute viewing distance and virtual depth. So this absolute viewing distance means if you're 2 meter, they're 2 meter away from the object. If it's 3, it's like this. So the virtual depth means the content was induced to provide the depth, like for the close one was the 0.4, the middle, and far. So we have like these 3 combination of virtual depth. So we have total of 6 conditions by combining these 2 independent variables. So the results. So in the perceived distance difference, we accept the hypothesis 1 that perceived distance difference increases as the virtual depth increases. And they reject the second hypothesis, the absolute viewing distance had no significant effect on PDD. So in the viewing angle threshold, the depth perception is permitted within a range deviating from the center by 23 degrees to 37 degrees. So we accept the hypothesis, the first one, the VAT significantly decreases as dV increases. We rejected the H2, the second one, direction had no significant effect on, virtual angle threshold. And actually, after conducting this, we also did the interview, and most participants says that when they just crossed the limit of their threshold, they just felt immediately lose their depth perception. It's not gradually decreasing, but just immediately, quickly, lost the perception of depths. So that was quite interesting finding. And the last one, the perceived presence, we can all accept these like realness, spatial perception, visibility, all decreases when the users go closer to the wall display. So the discussion, I could accept like these hypotheses. You can take more details in our paper. And through this, there are 3 design implications. The first is the content placement correction considering depth underestimation. So most participants, as already many research have shown, that they tend to underestimate their depths when they're in virtual environments. So we can find the same tendency in our experiment as well. And the second is the setting the depth perception zone using the viewing angle threshold. It might always differ from the condition, but by distinguishing this, we can like have some zone for it. And third is balancing the virtual to actual space ratio for maintaining the presence. So the conclusion and the future work is we like first explore the methods for experiencing sure depth perception using only wall display without any HMDs or tracking. And as the virtual depth increases, the users perceive distance as close and actual, and the acceptable viewing angle for depth perception narrow, and overall presence tend to decrease. The future direction we should more investigate about this group interactions and also group-based adaptive system to display this. So that's it, and thank you for your attention.
Okay, so we have time for a couple of questions. Do we have any questions from the audience? Okay, we have one question.
Thank you for the great presentation. Hyun from Seoul National University. So I'm curious about some kind of applications of this research. So you have demonstrated this application in exhibition scenario. But I think the technology that you have presented has some kind of more potential to be applied in other kind of scenarios like collaborative data analytics, etc. So I'm curious about your insights about the further application of this.
Thank you for a great question. So through this, the most interesting thing was the viewing angle stretch, the viewable angle, which can pursue the depth perception was quite wide. So not only for just like this 3D contents visualization, but also we can use for, like, as you mentioned, later visualization in many things. And I'm also thinking about kind of hybrid system with HMD and wall display, using them together. So in somehow we can, to be honest, have like bunch of scenarios, but now on I'm focusing on more some immersive content and exhibition things. But after that, what I'm really willing is that even if without HMD, that people can interact with some extended virtual spaces, so we can even show some the other place by through this wall display or some contents, etc. So that's what application that I'm looking about.
Okay, we have time for another question. Okay, then maybe I will ask one question. So for your BAT, right, you said this was a categorical variable where you asked the participants whether they were perceiving depth or not, right? This was a yes or no, and then you were moving them around this circle on the floor. Did you use a specific angular changes to define that threshold, or how did you define what was the border between them being able to distinguish the depth or not?
So the method I use is I set the 5 degree, 5 degree as the step size for distinguishing, and as I mentioned, I use the staircase algorithm, which like kind of randomly says some the metrics, and through that just repeat it a couple times and figure out the threshold range of it.
So you obtain a just noticeable difference in your.
Yeah,
Okay,
that's right.
perfect. Thank you. Oh, we might have time just for a quick question. That should be a quick question.
Hi, it was a good presentation. Thank you for that. My question is regarding, so your research specifically was on the viewers standing still, right? And can you like speculate what will happen if if the viewer has to like do some task or interaction? Maybe will the results still apply?
Yeah, I think it's gonna still apply. And I guess through my other research about some redirected walking, which is also related with the perception, in that case, if there's some like environmental condition is more complex, or if you're conducting something, they mostly use your like, we're focused on that task as well. So what I'm imagining is maybe it's gonna be more extended, I guess, because they're gonna focus on the task into it. And well, but if these multiple people are participating together, someone who is not doing that interaction might be narrowed down. But for now on, I'm not sure about it. I think that's a really good next step to conduct.
Thank you. Thank you.
Thank
Mhm.
you.
Let's thank our presenter once more. To close our session, so we have Sonwei Ya from the Beijing Institute of Technology in China, presenting the paper Improving Pointing Accuracy for 3D Target Selection in Virtual Reality through Depth Perception Biases Correction.
Good afternoon, everyone. My name is Songyue Yang, a PhD student from the Beijing Institute of Technology. I'm honored to be here at ISMAR to present our work titled Improving Pointing Accuracy for 3D Target Selection in Virtual Reality through Depth Perception Basis Correction. In VR, precisely selecting target in depth is very hard. Many of us have experienced this. Your heart often overshoots or falls short. The reason is the consistent error in how our brain sees depth in VR. A key problem in VR headsets is the Vergence accommodation conflict, or VAC. This conflict tricks our brain into misjudging distance, and we usually think things are closer than they really are. This error in what we see makes our pointing less accuracy. Now, pointing model like the ternary Gaussian model work very well for 2D screens, but when we use them in 3D, they aren't very good at predicting depth along the z-axis. The main problem is that those models ignore the consistent errors caused by the VAC. So our work tackles this problem head on. We believe that to make the prediction model more accurate, we must include the efforts of those depth factors like the VAC. To solve the problem of pointing uncertainty, a lot of past research has tried to model and predict where the user's hand will land. While 3D pointing models have advanced our review-related 3 unsolved problems. First, they are still not accurate enough when predicting depth along the z-axis. Second, they overlook critical perception bases caused by the philosophical factors like the VAC. And third, the effective range is too short for modern VR systems and that use redirection technology to extend the interaction up to 2.5 meters. Those limitations led us directly to the core questions that drive our research. So our main goal is build a 3D pointing model that corrects for those depth perception bases and stays accurate over a long range. Our research follows 4 clear steps, measures the basis, model the basis, correct the pointing model, and finally evaluate. Those steps form the 3 key contributions of our paper. We model near-field depth perception basis. We analyze pointing performance in various 3D motions up to 2.5 meters. We integrate our basis model into the ternary Gaussian framework to improve its accuracy. To build our new model, we first need to measure and understand the depth perception basis. That was the goal of our first experiment. Our main idea was lighting models are not very accurate because user can't see depth correctly in VR in the first place, most because of the VAC. You can see the setup here. Our main method was to remove all extra depth cues until only the core binocular cues were left. Here's how. We got rid of all information like occlusion, texture, and shadows. To stop motion parallax, we put the headset on fixed mechanical arm. We also circled the target so it looked like the same size at all depths. By doing this, we made sure the only depth cues left for people to use were convenience and binocular disparity. The text was simple to, The result from the experience one clearly showed the patterns of depth perception basis. The plots at the top show that as depth increases, the curves get wider and flatter, meaning more uncertainty. We have 3 main findings. First, the perception bases get bigger and distance. Second, we saw a strong VAC effect. The bases were smaller at 0.6 meters, which is our headset's focal plane. This provides a strong evidence and that the VAC is a key cause. Most importantly, we found that up to 1.5 meters, the bases follow a predictable, almost Gaussian shape. Beyond that, binocular cues become more effective. This is a model we developed, which we call P of X and D. It predicts the probability of user experiencing a depth basis of X at a target depth of D. We use a bell-shaped curve model where the key parameters, the peak, center, and width, are all functions of the depth. The figure on the right shows our model's prediction curves, which successfully match the experimental trends. This model is the key part we will now use to improve the 3D point model. Now that we have measured and modeled the user's perception basis, we can move to experiment 2. Our main goal here is add this basis model into a standard 3D pointing prediction framework. To forecast our new model's performance, we designed a pointing experiment with a wide range of tasks. Because we are interactions and dynamic, we couldn't just use still targets. Instead, we broke down complex 3D movements into 3 basic motion types, as shown in the figure. First is motion in depth, second is the motion in plane, and the third combined motion. For each of 48 text conditions, we fitted the collection of user endpointings into Gaussian distribution. This practice let us distribute the overall pointing behavior using just 2 key parameters: its center, which is the mean error mu, and its spread, which is the standard deviation sigma. This figure provides a complete overview of those mu and sigma values across all conditions. The key takeaway is immediately visible on the z-axis as target depth d increase both the error mu z and uncertainty sigma z grows dramatically while the x and y axes remain stable. This gives us a powerful first look, suggests that 3D pointing the main challenge is depth axis. To confirm and quantify the pattern we just saw, this next figure breaks down the data by each individual factor. Please focus your attention on the two columns on the left under depth D. This line plot makes the conclusion unmistakable. The green line representing the z-axis shows a dynamic trend where both error and speed increase sharply with depth, while the x and y axes remain flat. So our final goal was to build a model to predict those behaviors. We compared 3 models. The first 2 were baseline, adapted from work by Yu et al. And Huang et al. However, neither could fully explain the large perceptual errors we observed. This led to our model 3, the perception-based correct model. The key idea is simple. We take a standard pointing model and add a perception correction part. This correction uses the error function mu d and sigma d that we derived from experiment 1. Importantly, we use a weighting function omega d to apply this correction strongly in the near field where it's most needed and fade it out at a further distance. The table here shows a head-to-head comparison of all 3 models, and the result clearly showed that our approach is superior. To conclude, our work shows that depth perception error in VR are predictable problems caused by the VAC and weakening binocular cues. Depth is the mean score of uncertainty in 3D pointing. By modeling this error, our new model greatly improves prediction accuracy along the depth axis. Of course, our work has limits. The model is device specific, and we focused only on binocular cues. Our future work will extend this model to other headsets and add more cues for greater distance. This concludes my talk. Thank you.
Okay, do we have, okay, it seems that we have one question on the right-hand side.
It's a very interesting fun about the 0.1 meter focal plane for the HTC Vive Pro. Could you elaborate on that? And much of the literature states that the fixed focal distance for commercial headsets is typically further, such as it's cited around 1.5 to 2 meter. How do your finding relate to this?
That's a great question. Thank you. You are right. Other studies often say the focal plane is further away. Because of this, we decided to test our special handset ourselves using a standard method instead of relying on general numbers. We found its focal plane was at 0.6 meters. Our experiment results backed this up because we saw the smallest perception error happened right at that 0.6 meters mark. So this brings up a key point. Our error model is tied to the specific headset we used. We mentioned this as a limitation in our paper. In the future, we plan to test more headsets to see how they differ and to help build a more general model. Thank you.
Thank you for your answer.
Do we have any more questions? Okay, then with this, we're closing our today's session. Please remember we have a coffee break, and then after the coffee break, we will have a very interesting panel. It will be hosted this same room. So if you're interested, please come and attend, because that's becoming a serious concern in the community. So we will talk about what's the future of peer review in extended reality research. Okay, so thank you very much.
Okay.